Welcome everyone. We're going to do the corrections for the Math 85 pre-test in this video. So my hope is that when you went through some of these questions, there were things that were familiar, but if not, I'm hoping that this video will help give you a bit of a kickstart and refresh your memory. So let's take a look at the first question where it says simplify. When you see a question that says simplify, it often means we want to get rid of the brackets and put as many of the like terms together as we possibly can. So in this particular example, you have 2x cubed y all raised to the fourth power. Now this fourth power on the outside needs to attach itself or be given to everything inside those brackets. So you want to imagine applying that fourth power to the x, to the y, and to that coefficient of 2 out front. So essentially what we end up with here is 2 to the power of 4, x to the power of 3, but you have to multiply that by 4. We've got power of a power. So 3 times 4 gives us x to the power of 12, and then we have y to the power of that little imaginary 1 times 4, or power of 4. From here, you can evaluate 2 to the power of 4, and that really is 2 times 2 times 2 times 2. So 2 to the fourth power turns out to be 16, and we have x to the power of 12, y to the power of 4. Now again, if you weren't sure how this power rule works or power of a power rule works, you could imagine expanding the original question. So you would have 2x cubed y times 2x cubed y times 2x cubed y times 2x cubed y again. If you were to multiply all of these together, 2 times 2 times 2 times 2 is 16 one more time. X cubed times x cubed would be x to the 6th. When you multiply that by x cubed, you'd get x to the 9th, and then x to the 12th, that final x cubed. And then y times y times y times y would be y to the fourth power. So you can think of this both ways, but when you have a power sitting outside the bracket and you've got a term on the inside of the bracket, as we did in this example, you bring that power inside and apply it to everything inside those brackets. Okay, let's take a look at our second example and see how this differs slightly. So once again, we're asked to simplify, which means remove the brackets and try and collect any like terms if possible. Here we have a single term of 3 being multiplied by x squared minus 4x. So essentially we need to distribute that 3 through the bracket. So we're going to multiply those two terms by 3. Now 3 times x squared is going to give us 3x squared. Then we have 3 times a negative 4, so be mindful of your sign. 3 times negative 4 is going to give us negative 12, but we still have that x that we're multiplying by, so we leave that as negative 12x. But when we look at the next set, we're subtracting 5 times x plus 2. So we're actually going to distribute that negative 5 through the second set of brackets. So negative 5 times x is going to be a negative 5x, and negative 5 times 2 is negative 10. From here, we have 4 different terms, but 2 of them can actually go together because they're considered like terms. So negative 12x and negative 5x are like terms, so we want to combine those like terms. So if you have something like this, we want to make sure that your answer is written in descending order of power. So we want to start with the highest power, which in this case is that 3x squared, power of 2. And then we're going to combine negative 12x and negative 5x, but this just becomes an exercise in subtraction. So negative 12x's minus 5 more is going to give us a total of negative 17x. Now that constant at the end, that minus 10, doesn't have any like terms, so we can leave that as the final term in our simplified answer. So our final answer here is 3x squared minus 17x minus 10. Example number 3, we continue with that simplify set of instructions. So this time, although there are 2 sets of brackets, as there were in the second example, the one we just completed, these 2 sets of brackets are side by side. So essentially we need to multiply these things together. So yes, we have to distribute the negative 2 out front, but we also have to take these 2 binomials. So they're called binomials because there are 2 terms in each set of brackets. We have to multiply these 2 binomials together before we distribute the negative 2 out front. So my piece of advice is to what I call FOIL first. FOIL is an acronym that helps us decide what we need to multiply by when we have two terms multiplied by another set of two terms. So I'm going to erase this line underneath for a second, and we're going to start the FOIL process. So because we're not going to touch that negative 2 out front, I'd like to leave that, and we'll multiply it through a little bit later. So just rewrite it so you don't lose it as part of your work. Now, when we actually start the FOIL process, the F in FOIL stands for first. So what that means is we're going to multiply the first term in the first set of brackets with the first term in the second set of brackets. So 2x times x is going to give us 2x squared. Then we go to O, or outer. It means we're going to multiply the two outer terms in those brackets. So in this case, that's 2x times a negative 3. Be careful with your sign. So 2 times negative 3, I always worry about the numbers first. 2 times negative 3 is going to be negative 6. And again, we've got that x hanging on, so we've got to maintain negative 6 times x as your outer term. I is for inner, so we have 1 times x on the inside, so there's your I. 1 times x is just a 1x, and you can put that 1 in as a placeholder, or you can ignore it and just say plus x if you like. And then L is for the last term, so the last term in both sets of brackets. So positive 1 times negative 3 is going to be a negative 3. Now from here, we know we still have to multiply negative 2 through those brackets, or your choice is to actually combine some like terms in the next step if you like. So we've got negative 2 out front still. 2x squared doesn't have any like terms, but negative 6 plus 1 is going to give us negative 5 of those x's. We still have minus 3 at the end of our series here for our constant, but we're not quite finished with this question. The last thing we need to do is now distribute that negative 2, or multiply everything by negative 2 sitting inside those brackets. So once you do that multiplication, the brackets are removed. Negative 2 times positive 2x squared is going to be negative 4x squared. Negative 2 times negative 5 is a positive 10 of those x's, and negative 2 times negative 3 is going to be positive 6. So this ends up being your final answer in simplified form because we've removed all of the brackets through multiplication and we've collected all of your like terms. So our next example, example number 4, is again asking us to simplify, but this requires understanding of some of our exponent rules. So exponent rules are very particular, and we're going to get into 2 specific exponent rules with this example. What we see that's a little bit strange is a negative exponent. Now, negative exponents are legal. It's okay to have a negative exponent. Sometimes it's just considered bad form. So what we want to do is reposition exponents that are negative to make them positive. And in order to do that, you essentially slide those things across the division line. So I always say if you're in a negative space, you pack up and you move. So I'm going to highlight, in this case, the x to the power of negative 3, because that is a base that has a negative exponent attached to it. What we want to do is reposition that x to the power of negative 3 to make it positive. In this situation, because it's in the numerator right now, moving that into the denominator is going to make it positive. So 7 is perfectly happy where it is in the denominator. X is to the power of positive 1, so we leave that alone, but that x to the power of negative 3 crosses and joins it and becomes x to the power of positive 3. So all I've done is I've repositioned that negative exponent to the denominator to make it positive. Just as an aside, if it started in the denominator as a negative exponent, we would move it upstairs into the numerator to make it positive. So that's our first step here, but we're not quite finished. We're multiplying the x and the x cubed together. When you multiply bases that are the same, you have to add the powers. Don't forget, though, that if you have just an x all by itself, it's got a sneaky power of 1 sitting there. So x times x cubed is going to be x to the power of 1 plus 3, or x to the power of 4. I can't reduce this fraction any further. 2 over 7 can't be reduced. I don't want to make that a decimal number. Fractions are your friends, so leave the fractions alone. And there are no more x's that we can combine, no other variables. So this is completely simplified. Question number 5 has a different set of instructions for us here. We are asking you to factor the following expression completely. This looks like it's been simplified already. You've got x squared plus 3x minus 28, and that's true. It's in simplified form. Factored form means we want to take something and break it up into two multiples or into multiples. So we want to kind of reverse that FOIL process. In previous courses, whether that was Math 75, Math 10C, or a Math 10C equivalent, we have whole units on how to factor. There are all kinds of factoring techniques based on the type of polynomial you see in front of you. So this is what we call a simple trinomial. So you've got x squared plus 3x minus 28. You've got three terms, making it a trinomial. It's considered simple because the x squared up front has a coefficient of 1. It's just a 1x squared, and that makes our job for factoring a little bit easier. So whenever you see a simple trinomial, if it's factorable, we're going to be able to break this up into two binomial pieces or two sets of brackets. What I tell my students is always start with the first term first. I need to multiply my first two positions to get x squared back. So the only way that can really happen in this case is x times x. So if I were to FOIL this out, x times x would give me back that x squared. Now comes the tough part. Those last two terms have to multiply to give us a result of negative 28, but they have to add, so the numbers that we choose have to add to give us a positive 3. So this is where you need to think about factors of 28. So what numbers multiply to give us 28? Well, 1 times 28 multiplies to give us 28, but that's not going to sum together to give us a positive 3. So aside from that, 2 times 14 is 28, but once again, I can't combine a 2 and a 14 to get a total of 3. The other factor we get to work with here is going to be 7 times 4. And if we combine 7 and 4 the right way, we know that we're going to get a positive 3 in the middle. So I'm going to put a 7 times 4. Pardon me, I'm going to put 7 times 4 here, and we have to figure out how to multiply to get a negative, but sum this together to get a positive. And I'm actually going to make a mistake on purpose here to show you how you can check your work as you go. So when we take a look at our signs, if we multiply to get a negative, we know that one of these signs has to be positive and one has to be negative. So I'm just going to put down a negative 7 and a positive 4. Now, don't be afraid to use trial and error with factoring. The more you use trial and error, the quicker you're going to get at the answers. What I've done here is I've switched colors to show you a little check. I know x times x is x squared, so my first term works. I know that negative 7 times positive 4 is negative 28, so my last term works. It's the middle one that's finicky. That's the one we have to be careful with. So if I do something I call a SMILES check, it's a really silly name, but you'll see how it works here in just a second. So if I multiply negative 7, whoopsie, I've erased here. If I multiply negative 7 times positive x, we get negative 7x. If I draw a big smile and I multiply x times positive 4, I get a positive 4x. When I combine those two terms, I end up getting a negative 3x, but we really want a positive 3x in the middle because that's what our original expression was. What that tells me is just that my signs are backwards. So if I go back and I change my signs, and I'm just going to rewrite a new version of this expression over on the right side here. So if I factor instead as x plus 7 times x minus 4, if I were to do my SMILES check, I'd get a positive 7x as my baby smile. I'd get a negative 4x as my big smile when I multiply those terms together. And 7 minus 4 would give us a positive 3. So x plus 7 times x minus 4 is the factored form, the proper factored form for this expression. Again, the way we did this originally, those signs didn't work, so that's not correct. This is our new correct answer. Factoring is going to be an essential skill in Math 85. So if you're having trouble factoring or if you're rusty on different types of factoring, we need to make sure that you're up to speed by the time we get into Module 8. The next question asks for something very different here. It says solve. We're not factor anything. We're trying to solve this equation. So in order to solve, what that means is we're saying get x by itself. What does x equal, or what is x equivalent to? So if we start with 3 times x plus 1, and that's set equal to 2x minus 4, all equations will start with equal sign somewhere in the middle. What we need to do first is get rid of the brackets on the left-hand side. So let's open them up by multiplying 3 through. So 3 times x is going to give us 3x. 3 times positive 1 is a plus 3. So that's going to be set equal now to 2x minus 4. Again, we want x's to one side and numbers to the opposite side. So I'm going to move 2x over to the left. And in order to do that, we have to do the opposite. So technically, we're adding 2x right now. So to reverse it, we're going to subtract 2x from both sides. So if I subtract 2x from the right, it disappears. If I subtract 2x from the left, it becomes 3x minus 2x. We're going to do the same thing and move the 3 over to the right side. So we've got a negative 4 on the right side already. When 3 joins it, again, we have to do the opposite. Plus 3 to undo that relationship means we're going to subtract 3. So if we subtract 3 from both sides, our equation now looks like this. So 3x minus 2x is a single x. Negative 4 minus 3 more puts you further into negatives. You've got a negative 7 altogether. So that is the solution to your equation. If you were to check that solution now, we could substitute negative 7 in for x, and I guarantee the left side would equal the right side. Question number 7 is also a solve problem, but this one differs a little bit. If you have an equation that's quadratic, which means degree 2, we've got x squared minus 5x plus 6, so that's set equal to 0. In this particular situation, we can't get just plain x's on one side and your numbers on the opposite side because we actually have an x squared and an x, so we can't combine those x's. What we need to do to solve something that is quadratic or higher than just a degree 1 equation is to actually factor first so that we can break these down into linear factors. So once again, we're going to do that reverse FOIL technique to factor first. So if we think about first two terms multiplying to give us an x squared, it's got to be x times x. Aside from that, we have to multiply to get a positive 6, but we need to sum together to get a negative 5. So I'm just going to jot that down in the margin. We need to multiply to get a positive 6, but we need to add those same numbers. Again, this is a simple trinomial to get a negative 5. If we need to multiply to get a positive, the only two ways to do that are a positive times a positive or a negative times a negative. In this case, we know it's a negative times a negative because we have to sum those together to get a negative 5 overall. Factors of 6 are either 2 times 3 or 6 times 1. In this case, the only way that our SMILES check is going to work is to make this a 2 times a 3. So at this stage, we have everything in factored form. You can double check your factoring to make sure that you're correct, but we haven't actually solved the equation yet. What we need to do now is make these two little mini equations and solve them individually. So if I told you that x minus 2 was set to 0 because of something we call the zero factor property, when I multiply these brackets together, I need to get 0 overall. So x minus 2 on its own could be 0, or x minus 3 on its own could be 0. So we actually end up with two solutions here. If I were to solve this first little mini equation for x, we have to move that negative 2 over to the right side, so we do the opposite. If it's x minus 2, to move that 2 over to the right side, we would add 2 to both sides. So x would equal 0 plus 2, or positive 2. With the second set of factors here, x minus 3, once again we have to move that 3 over to the right side, and doing so we have to add 3 to both sides. So if we do that, we get 0 plus 3 on the right side, or positive 3. In this case, we end up with two solutions. One is x equals 2, and the second solution is x equals 3. Now we want to switch gears for number 8 and talk about the slope of a line. Now, right now, the equation that we're given is 5x minus 4y equals 10. That's in what we call standard form. If we manipulate this equation into slope-intercept form, then we can read the slope and the value of the y-intercept quickly and easily. In order to do that, we need to make this look like y equals m times x plus b. So essentially, we have to rearrange this equation and solve it for y. Aside from that, we need to make sure that we're reading the slope as the coefficient of our x value. So the first thing I want to do to isolate for y, or to solve for y, is move that 5x over to the right side. So negative 4y stays in play. You'll have negative 4y, and that's set equal now to negative 5x. We're going to subtract 5x from both sides, but we still have plus 10 or positive 10 on that right side. From here, we want to isolate y further by dividing everything by negative 4. And yes, you can divide a whole side by negative 4, or I find it easier in this case, because we're looking for slope, to divide your terms individually by 4. So if we clean this up now, we get y equals, on the left side, a negative 5 divided by negative 4 is positive 5 quarters times x. Now we've got minus 10 over 4. So you can reduce that 10 over 4 because you can divide them both by 2. And you can say that that's actually 5 over 2 in reduced form. What we're looking for, though, is the slope. And remember, the slope is the coefficient in front of the x. So whatever's in front of the x is representing our slope in this case. So 5 quarters is that coefficient in front of the x. So we know that for this particular line, the slope is going to be 5 quarters. Please make sure that you're just giving us the numeric value and you're not including x with your slope, because that would not be correct. So our slope is just 5 quarters. Our next equation is slightly different. It's still a linear equation. We have y equals negative 3x plus 7, and we're looking for the y-intercept this time. It's already in slope-intercept form, y equals mx plus b, and we know that the b value, or the constant, is always the y-intercept. This line has a slope of negative 3, but the y-intercept is positive 7. So if we want to write that as a proper ordered pair, we'd say when x is 0, your y value is positive 7. So they've actually written this equation for us in a form that's user-friendly. Now, if you weren't sure about the y-intercept, here's an alternate way to figure this out. We know that every y-intercept in the whole wide world has an x value of 0. So if I let, let's try this again. If I let x equals 0 and I solve for y, then we get y equals negative 3 times 0 plus 7. Again, the reason why I know to do that is because every y-intercept in the whole wide world has an x value of 0. Now if I clean that up, negative 3 times 0 is 0. 0 plus 7 is positive 7. So we get the same value for a y-intercept, whether I use a substitution for this linear equation or whether I look at this equation in slope-intercept form. So slope-intercept form is really useful for linear equations or degree 1 equations. The algebraic way for us to make those substitutions is going to be more valuable when we get different kinds of equations, and maybe equations that aren't linear. So again, 2 different ways to find the y-intercept for this example. So last but certainly not least, we have an inequality to solve. So it's kind of like solving an equation, but instead of an equal sign, there's either a less than or a greater than symbol. Sometimes it's less than or equal to, or greater than or equal to. So we're going to start with our inequality. 4x minus 6 is less than 9x plus 9. So what we want to do is, again, get the x's to the same side. So if I move my 9x to the left side and my negative 6 to the right side to join the constants, or just the numbers, we'll have 4x minus 9x, because we would have to subtract from both sides. And that's still less than 9. When 6 joins it, we're going to have plus 6, because we have to add 6 to both sides to balance the inequality. So from here, 4x minus 9x, we collect those as like terms, becomes a negative 5x, and that's less than 9 plus 6, or positive 15. From here, what we want to do is actually solve for that x. We want to get that x by itself. So I'm just going to rewrite this up here on the next side of our screen. We've got negative 5x is less than 15. What we need to do is divide both sides by the coefficient of x, in this case, negative 5. But something funny happens when you divide or multiply by a negative number and it's an inequality. When you multiply or divide by a negative number, the inequality actually has to flip. So we've got x, and instead of less than 15 divided by negative 5, we now need to flip that sign and say that it is greater than 15 divided by negative 5. And if we work that out, it's negative 3. So one of the rules we need you to remember here is that whenever you multiply or divide an inequality by a negative sign, you have to flip that inequality. Its direction needs to change. Underneath here, I'm going to explain a really brief scenario about why that happens. If I were to give you the inequality 2 and say that that's less than 10, we agree that that's true. If I multiply both sides, let's say by 5, just as an example, remember, whatever we do to one side, we do to the other side. What we'd end up with here, 5 times 2 is 10, and yes, that's still less than 10 times 5, which is 50. So multiplying by a positive doesn't change the result. But if I start with that inequality again and say 2 is less than 10, and this time when I multiply, I'm going to multiply by a negative number. So let's say we multiply by negative 5. If I were to work this out now, negative 5 times 2 would be negative 10. 10 times negative 5 is negative 50. But negative 10 is actually bigger than negative 50. So if I left that as a less than symbol, we would be incorrect. So that's why when we multiply or divide by a negative number, the orientation of this symbol needs to change to make it true or make it accurate. So again, when you multiply or divide by a negative number and you have an inequality in your expression or in your equation, you want to make sure that you flip those signs. That's the end of our corrections for this pretest. If you have any questions over and above what you've seen here, please don't be shy. Come and see me and we can help you get things sorted.